Okay, so you guys should have already turned this problem into us 2004 for response number 5. It's a non-calculator problem. Are you kind of getting in the zone of these yet? Like you have a picture. It's a fundamental theorem of calculus problem. They're on non-calculator parts of the exam. We're hoping you're kind of getting the hint of these. So this problem says for the stem, the graph of the function f shown above consists of a semicircle. So they're just wanting to make sure you understand that that's the bottom half of a circle and 3 line segments, so 3 different portions of diagonal lines. Let g be the function given by the integral defining function g of x equals the definite integral from -3 to x of f of t dt. And remember that this was a graph of f, which Mr. Harney already drew my nice graph for me and labeled it as a graph of f. So this has a part A, B, C, D. So part A says to find g of 0 and g prime of 0. So because we are hoping you're getting into the groove of this fundamental theorem of calculus kind of problem, I'm hoping that you realize, okay, if I have an integral defined function, because I know at some point I'm going to use it, I'm going to take the derivative of both sides. So the derivative of g of x would turn into g prime of x. And wouldn't the derivative of the antiderivative, right, if I wrote like that d over dx notation, wouldn't really this cancel this, and the x would replace the t, and the derivative of the antiderivative is just the function. We don't have backwards boundaries, we don't have chain rule, we're just replacing it, and g prime of x equals f of x. So really, this graph of f is the graph of g prime. Okay, and you want to mark that on your graph. So when your graph is given to you on your AP exam, like you want to add those like extra pieces in. They're not going to care if you draw on the graph. So part A, we want to find g of 0 and g prime of 0. So g of 0 just means go to the rule that they gave us for g in terms of x and replace every x you see with 0. So -3 to 0 of f of t dt. Well, -3 is smaller on the bottom boundary than 0 on the top for our upper boundary. So don't we want to sweep out the area from -3 to 0? That is this function tau underneath this f graph, which is the graph of g prime. Well, I don't know what you guys see, but I see a trapezoid. So here are my parallel bases, and this is my height across the x-axis. So my height is 3. This is a -3, -2, -1, right? Count 1, 2, 3, height of 3. So that's what I would think. I would think, oh, it's 1/2 the height times the sum of the bases, and I would be calculating the area of a trapezoid. The location of that is above the x-axis, so I'm going to accumulate a positive answer. 1/2 times 3. This base is too tall. Be a little cautious and not accidentally use the x value. It's the y value, how tall that base is, which is 2. So this is like a trapezoid like we did when we were doing car calculus. And this base is 1 tall, and 2 plus 1 would be 3, and times the other 3 would give me 9 on top. It doesn't reduce nicely. I would just leave it as 9/2 and move on. If you wrote 4.5, that's the same, but you could honestly stop it here too. But I went ahead and multiplied that out for that one with it, thinking about like it being the area of trapezoid. I went ahead and multiplied it out to the area of trapezoid. So g prime of 0, finding the derivative evaluated at 0. Well, remember, we've already established by fundamental theorem of calculus that g prime of x equals f of x. So the best notation is g prime of 0 equals f of 0, replacing every x you see with a 0. Oh, and that just means, where am I on the graph of f at 0? Oh, at 0, I'm at 1. So there's part A. Okay? Part B says, find all values of x in the open interval from -5 to 4. Well, that makes sense because our graph goes from -5 to 4. It does say in the open interval, at which g attains a relative maximum. So we've had ones that say local, we've had ones that say relative, but if it's a relative min or max, you're trying to think about that first derivative test and the way the derivative changes sign. So if we're thinking relative maximum, aren't we thinking about where the derivative changes from positive to negative? So the original curve would change on the original function from increasing to decreasing, and that result would be a maximum extreme. And it does say justify your answer, so that means we're going to have to write some stuff out in words. So if this is the graph of g prime, this is the graph of my derivative, and I've already established that, so the readers will keep reading that on all the other parts of the problem with you. Then I'm looking for where this graph changes from being positive to negative, so above the x-axis to below. That's the wrong direction. Here we don't change sign, even though the derivative equals 0 at 1, we don't change sign before or after 1. And it looks like the only spot we have is 3. So f prime, which equals, no, not f prime, g prime, which equals f, changes sign from positive to negative at x equals 3. Therefore, our original function g has a relative maximum at x equals 3. Or if you reverse that and you said g has a relative max at x equals 3 because g prime, which equals f, changes sign from positive to negative at x equals 3, that's fine. You can flip it around and say this happens because blah, blah, blah. The best way is this is happening on the derivative, which results in this. Okay? So that was pretty quick because they only asked us for a relative maximum and not anything to do with minimum. Part C, find the absolute minimum value. Oh, that means I want to find the minimum value, the y value of g on the closed interval from -5 to 4. Again, aren't we getting used to this part of this problem? And justify. So here's our extreme value theorem. So our derivative is defined everywhere. That means it's differentiable everywhere. If you're differentiable everywhere, it implies you're continuous everywhere. So the original g must have been continuous, and that's really all you need to have for your hypothesis. So g is continuous on the closed interval from -5 to 4. And then doesn't that mean EBT applies? I don't know that they actually expect on EBT problems you to state the hypothesis. That is the hypothesis.
Yeah, they've said before that your justification is just doing the candidates test.
So let's list out our candidates so we know which ones we're going to be testing, right? So we have our endpoints, x equals -5 and x equals 4. And then remember for this part, they didn't need both set of absolute extrema. They just wanted the absolute min. So in order to have an absolute min, it could be from the endpoints. And it could be from where the derivative equals 0 and changes the right way to even have a local min, which would be from negative to positive, or anywhere where the derivative is undefined. Because this is the derivative and it's defined everywhere. There's values everywhere between -5 and 4. So we're really just looking for where the sign changes the correct way from negative to positive. So is it that at the -4 spot? This one that we were just talking about was a relative max or a local max. So how could that be an absolute min? So this one's out. And at 1, you don't change sign. So it looks like the only other spot we need to consider is -4. And I'm going to write out because this is where g prime, which equals f, equals 0, and switches from negative to positive. Because you have to change that way to have a local min before you can even have absolute. Uh-oh, I'm doing the Herney writing crooked thing. All right, so now we're going to test them. So we're going to test them into our integral defined function. So this is a more typical problem where you do have an integral defined function. So the notation's like a little cleaner. I'm going to replace the x with -5. I'm going to start with that endpoint. So it would be the definite integral from -3 to -5 of f of t dt. Uh-oh, though, -3 is really bigger than -5. So the best notation would be to show them, you understand, that's going to negate the normal answer if we just went from -5 to -3 for the area underneath our curve. So -5 to -3. Well, that would be this triangle below, but this would be this triangle above. They're the exact same right triangle dimensions down to up to for the height. So one of those cancel to 0. So it doesn't even matter that I'm really negating anything if I end up having things canceled. So that one actually goes to 0. So the next one I'm going to try is my other endpoint, which is +4. So g of 4 would equal the definite integral from -3 to 4 of f of t dt. So from -3 to 4. So that's a ways, guys. So we already have the trapezoid from -3 all the way to 0. This part under the curve and this part will cancel. So I don't really need that, but don't I need this part? which we had another problem that was kind of similar to this. In fact, when Bernie drew the problem on the board, he's like, didn't we do this problem already? Because sometimes they look so similar. But it's like this triangle curvy piece. Isn't that really that idea of, hey, you got to find the whole rectangle area, subtract out the semicircle area, like if I can cut it out with scissors, so I just have this curved portion and this curved portion that's left. So this is a little harder. Boundaries are normal, but it's just a little harder to accumulate that piece. So G of 4 is going to equal our trapezoid part first. Its location was above the x-axis. We already found that answer in part A, which was 9 halves when I went ahead and reduced it all. The next part is still above the x-axis, so I'm still going to be adding, but to get that next part, I'm going to use some notation, some parentheses, and say, oh, it's the area of the rectangle minus the area of the semicircle. So my rectangle has a base of 2, a height of 1. So 2 times 1 will give me 2, minus a semicircle is a half circle. So this is 1/2 pi times r squared. My radius is 1, no matter which way you think about it. And 1 squared would stay 1. So I would actually stop right there. Like, it's all numbers, it's full credit. You don't need to get a common denominator, blah, 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 blah. If some of you would make this pi over 2, that's fine. But you're done. That would leave you with those little curvy triangle pieces. Okay, so now we're looking for the last one, which is -4, and then we'll compare them all. Remember, we are looking for absolute min. So it might be like, well, no, Mr. Ryan, I have to like figure this out. But no matter what, like, you guys, 9 halves, right, is 4.5. You're adding 2 to it, so now you're up to 6.5, and you're subtracting 1 pi over 2. This is like a big positive number. This one's 0, so it's definitely less than that one. So I'm thinking this one's not going to be it if we're looking for absolute min. So the last one's g of -4. So g of -4 would be the definite integral from -3 to -4 of f of t dt. Oh, once again, we have backwards boundaries. So we're going to have to negate this, flip it around, -4 to -3 of f of t dt. So g of -4 would equal the negative sign in front, and we need to accumulate from -4 to -3. So that's a triangle that's above, it's a right triangle, above the x-axis, a base of 1, a height of 2, so 1/2 times 1 times 2, which will give us what? -1, which is the smallest of them. So therefore, G has an absolute min of -1 that occurs when x equals -4. You have to tell them which one you're choosing. They're not going to assume that you know what is biggest and what is smallest if you don't tell them. So I'm going to go through the points before I erase, because obviously these problems always take up so much space with the EBT part. So the points for this problem, when you're thinking about how you scored out of 9, you can maybe like look at this now and know where you got the points and where you missed the points. You got 1 point for finding the 9 halves. You got 1 point for finding that g prime of 0 equal to 1. So part A was 1 point for each thing. If they ask it like that, sometimes they'll ask you like g of 0, g prime of 0, g double prime of 0. It's 1 point for each one typically. You get 1 point for your answer, that you had a relative max at x equals 3, and then 1 point that you justified correctly for a local justification on part B. Part C is the EBT part, so you get 1 point that you considered using -4. You got 1 point for your answer with, you got 1 point actually for getting -1 for g of -4. So if you got that answer, they gave you a point. If you like knew to use that one and eventually got the right y value, and then you get 1 point for knowing that that is the correct one with your EBT justification. So you like ran all your other candidates to prove that that was the smallest. But in that one, some people might have struggled on this one, but like at least if you got that one, you got a point, which was kind of nice of them to do. a little bit. But to get like the full credit, you had to make sure you tested the other ones and proved that that one was the smallest.
I just want to point out one thing. So over here, you had to find g of 0 and g prime of 0. A lot of times they will ask you to find g double prime of 0. If you had to on this one, g double prime would be undefined because your slopes are coming to a cusp or corner. Remember, you can't differentiate at cusps and corners.
So the second derivative is undefined because there's a corner on the first derivative graph. That was a really good thing to point out because we haven't had one that's asked that for a while.
No, I feel like that's more common on the newer ones though.
Yeah.
Well, they got to find like g prime, g double prime.
And actually, I'm going to be really bad and make D fit up here and not erase because I realized that the EBT was part C. So I'm going to make D fit right here because it doesn't ask us to justify. So it just says find all values of x in the open interval from -5 to 4 at which the graph of G has a point of inflection. So if I want to know points of inflection or inflection points, wouldn't I be thinking where the second derivative, G double prime, changes sign? If the second derivative changes sign, then that means the original function would change from concave down to concave up or from concave up to concave down. And a change in concavity means a point of inflection. So since we know already by fundamental theorem of calculus that g prime of x equals f of x, and now we're going to talk about the second derivative, how about we take the derivative of both sides of this? So g double prime of x would equal f prime of x, which means to look at the slopes on our f prime, which equals on our g prime graph, which equals f. Duh, right? So we're looking at the slopes of the first derivative to think about the second derivative. So it's kind of like messy, but that's what we're looking at. So we want to know where our slopes change. Well, all of this interval from -5 up to -3, the slopes are all the same value actually. And they're all going to be what? Up 2/1. No matter what, they're positive, 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 positive. But down here, all of a sudden we're decreasing on the G prime graph, which means that if we're decreasing on the first derivative graph, the second derivative would be negative. All the little slopes here would be down 1/3. So didn't we change signs? So 1 point of inflection would be at x equals -3. Slopes are all negative, 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 negative. They stay negative. Right here, you're really not differentiable like we were just talking about. But you still have negative slopes here, so nothing's happened. But right at 1, oh yeah, we changed from decreasing on the first derivative to increasing on the first derivative, which means the slopes changed from negative for the second derivative to positive. So another point of inflection would be at 1. And then the last one would be at 2 because your slopes change from positive to negative on that first derivative G prime graph, which means your second derivative has changed sign. And that would be our answer for part D. Okay, so going through the points kind of quickly, we already did A was 2, B was 2, C was 3, which is pretty typical for EBT, which means all we have left for D is 2. And the rubric said you got both points if you had all correct values. And it says -1 for each missing or extra x. So this one was 2. So if you were missing 1, you would miss a point. If you were missing 1 and had an extra spot that was wrong, then you get nothing. Because you'd have 1 that was missing and 1 that was extra, and you missed 1 for each of those, and then you were out of the 2. So that's kind of how it went. But at least you could have got 1 out of 2 if you had hopefully just 1 mistake. Hopefully you had no mistakes on that and had them right, and you didn't have to justify. Any last minute thoughts on that one, Mr. Herney?
Nope, looks good.
Okay, so hopefully you guys are doing well and getting used to these fundamental theorem of calculus problems and improving. That's the goal.